All right, everybody, we have our next talk in this session, which is Anna Comesana talking about machine learning techniques for predicting properties of synthetic aviation fuels using Python.
Yeah. Hi, everyone. Thank you all for being here. Today we're going to be talking about aviation, which is one of the hardest sectors to decarbonize. And why is that? Well, you can't just strap a giant battery on a plane and just hope for the best, right? There's weight and safety constraints that make electrification pretty impractical for long-haul flights, at least for now. And so instead, synthetic aviation fuels, or SAFs, offer a pretty promising path forward. The problem is that the process to get a new fuel certified is pretty costly, time-consuming, and really high risk. And by high risk, I mean that candidates require really large volumes just for property testing. And we often don't know how well a fuel is going to do until pretty late in the process when a lot of money and time has already been spent. So today, I'm excited to talk to you about how we've been using machine learning to develop a faster, data-driven approach for fuel screening. One that allows us to anticipate key aviation properties pretty early in the development cycle to kind of help de-risk and accelerate the whole process of SAF research. I want to first acknowledge my team and thank them, both at Lawrence Berkeley National Lab and Oregon State University, as well as Oak Ridge National Lab for letting us use their computing facilities. And I also specifically want to acknowledge the Bioenergy Technologies Office for funding this research. And with that, let's start with a little bit of background into this project and how it came to be. Before SAFs can fly, they have to pass through a multi-year certification process where each candidate needs to meet really strict property requirements for things like boiling point or viscosity, right? And that alone can take hundreds of gallons and millions of dollars. And so that means that only a handful of SAF candidates get to make it to that stage of the process. And so we're really forced to make big decisions early on without really having enough data to know if it's going to work or not, which doesn't really reward experimentation. So to help with that, we set out to develop a way to estimate fuel properties much earlier in the process using using minimal material and also, no large-scale testing at all. And that led to feedstock to function. Now, feedstock to function is a web-based tool designed to support early-stage SAF development. As a first pass, a couple of years ago, we set out to predict properties of molecules using molecular descriptors. And those are things like number of carbon counts or just like topological features, things like that. And so we used those to predict the boiling point, flash point, melting point, net heat of combustion, and yield-suiting index of molecules. And that worked pretty well. And we published our results. You can see a little paper on there. And also built this cool little tool on the right to kind of integrate our data and models into. Now, a great thing about our approach is that it was not only able to predict the properties of molecules, but it also kind of allowed us to investigate the relationship between the properties that we were predicting and the structure of a molecule. So, for example, we found that packing-related descriptors were pretty important for the prediction of melting point, which kind of made sense because they are related to lattice stability, and melting point directly reflects the amount of energy required to kind of like disrupt the crystal lattice. And so that was kind of cool because it was a way to verify our models and also try to see if there were new relationships that we could tease out just from using machine learning. But our ultimate goal was to predict properties of blends and real-world SAF candidates. And blends are messy, right? They are a blend of molecules, and so they don't really lend themselves to molecular descriptors. So we had to come up with kind of a new approach, and that's kind of roughly what it looks like. To train models to predict properties of fuel blends, we first needed to identify a viable set of features and a way to represent these fuels. And then we should figure out how to clean and transform these features and select the best ones for each property. And the properties that we set out to predict here are boiling point, flash point, freezing point, kinematic viscosity, and density. And the slight change in properties there was really just due to data availability. Then after that, we just want to, train those models to predict the properties, and we want to make sure that we're able to once again interpret the results and see if we can tease anything out about the relationship between the properties and blend composition, and then we're happy. So let's dive a little bit deeper into each of these steps. Now, as I said, the first thing we had to do was find a viable set of features, and we ended up settling on liquid phase Fourier Transform Infrared spectra, or FTIR spectra. Now, FTIR spectra is widely used in the chemical characterization community as a way to probe the composition or structure as well as the quality of a mixture, or in our case, a fuel. And the way it works roughly is infrared radiation passes through a sample, and then different atoms and bonds absorb specific wavelengths. And so what we get is a spectrum that shows how much light was absorbed at each point. And so it's basically kind of a readout of the different bonds or functional groups in the sample. So for example, here's what it looks like for ethanol. And you'll notice a strong, broad peak around 3,300, and that's due to OH stretching, which is, a key part of alcohols. So check, that makes sense. And you'll also see a complete lack of like an alkyne peak in the middle towards 2,100, which again makes sense because there's no alkynes in ethanol. And so FTIR spectra really shows us what is there and what isn't, right? It's like a chemical fingerprint that is unique to each molecule, sample, blend, and it really shows you the functional groups and bonds that are present in there. And we specifically chose liquid phase FTIR spectra because it's fast, it's low volume, and it's more consistent. And you really only need a few drops of the sample, and unlike with vapor phase FTIR spectra, there's no like heating or pressure control component involved, and so it's a lot more practical for early stage SAF screening. And so that's great, because now we have a relatively easy and chemically rich way to represent our fuels. But that came with its own fun sets of challenges, because FTIR spectra in practice is kind of more of an art than a science. Historically, chemists are really just going to look at the overall shape and approximate location of the peaks to figure out what's in their mixture. So that means that there's a lot of variability that they don't really care about. And that qualitative flexibility works well in the lab, but that means that there's variability from instrument, from collection settings, or even from the environment in which you're collecting your data that nobody's really recording or caring about. And for machine learning, we kind of need something more consistent and more structured. And so we kind of designed a pre-processing pipeline around three main categories. The first thing we wanted to do was fix instrumental error and noise. Now, the raw spectra that we had baseline drift and some high-frequency noise. Thankfully, the baseline drift was not, it was uniform. It was not like sloped or curved, just kind of consistently elevated the whole spectrum. And so we just corrected that by subtracting the mean signal from the 4,000 to 3,600 region, which you can see all the way on the right. And we use that region because for our fuel samples, they just don't absorb anything there. So any signal that we would see would be noise. That's mostly for water vapor, I believe. And then we just clipped any negative values to zero because absorbance cannot be negative, and also kind of applied a moving average to reduce any mechanical noise without really distorting any key spectral features. And then we had to harmonize our data. Our dataset came from two different instruments, each with slightly different resolution and response profiles. And so, for example, one sample might record a value at 650.142 and another at 650.147. And so to make them comparable, we just kind of binned the spectra into consistent wave number ranges and just kind of merged locally similar regions, and also normalized each spectrum by its sum to focus on relative shape rather than the actual absorbance values, which, as I've said, can really vary between instruments. And then finally, we applied some chemically informed trimming as a first pass to reduce kind of the number of features and dimensionality of our data set. We removed the 2500 to 2000 region, the little red square in the middle there, which is dominated by absorption from the collection vessel rather than the actual sample. And then we also dropped regions where, again, based on fuel chemistry, we knew there would be no peaks, and kind of confirmed that those regions were flat. And so an example of that was the region that I mentioned earlier, all the way on the right. And so all of these steps kind of helped transform FTIR from a qualitative signal into a more structured and generalizable feature set. And the next step was figuring out how to turn the spectra, the clean spectra, into interpretable features and kind of trim the dimensionality of our data, since one spectrum is represented by a 4,000 dimensional vector. Now, traditionally, researchers have tackled this by selecting specific regions of the spectrum that they know correspond to certain functional groups that they like, and then kind of discarding the rest and only training machine learning models on those regions. But that manual approach kind of assumes that we know which regions matter, and also that we know all of the regions that matter, right? And that's a little presumptuous. It kind of risks overlooking unexpected patterns elsewhere in the spectrum that might be important, even if we don't truly know or understand how they relate to the properties. So we wanted a method that could automatically extract meaningful features across the full mid-infrared range, and to do so in a way that could preserve interpretability. Now, you all may be familiar with PCA, or Principal Component Analysis. It's a pretty common go-to for dimensionality reduction, especially in scientific computing. And the way PCA works is by just finding directions of most variance in the data, called principal components, and then just projecting the data onto those components to reduce the dimensionality. Here's the catch. PCA components can have both positive and negative values, right? And they often combine combine signals from all over the input space. And that's a bit of a problem for us, because FTIR spectra absorbances are always non-negative, and so negative loadings are not inherently as interpretable. And also, PCA components blend signals across the entire input space, and so they don't correspond neatly to specific functional groups or bond vibrations. Instead, they're just kind of mixtures that are a little harder to link back to chemistry. And that is what led us to non-negative matrix factorization, or NMF, which I'm a huge proponent of. NMF is a technique for breaking down complex data into a set of simpler additive components, and it comes with a key constraint that everything stays non-negative. And that's not always an easy fit for other kinds of data, but for us it's pretty ideal, because as I've been saying, FTIR absorbances are always non-negative, and so this actually works in our favor because the math kind of aligns with the physics here. What the constraint means in practice is also that each spectrum gets reconstructed as a combination of a few interpretable patterns, and that those patterns only add to each other. They don't subtract. So we're essentially building each spectrum from parts, kind of like a Lego set. And that's why NMF is also often described as a building block method or a parts-based method. Instead of like abstract directions that blend the whole spectrum, NMF gives us distinct spectral building blocks that show up across the samples, and then also tells us how strongly each sample expresses that pattern. Now, one important thing to note before I keep going is that before training NMF, we have to choose the number of components or spectral patterns that we want the model to find. And if we have too few, we could, miss some important structure. If we have too many, we risk capturing noise. And so this becomes a key hyperparameter that we tune during model development. And I'll talk a little bit more about that later. Now, mathematically, NMF approximates a data matrix X, which is our FTIR spectra, as the product of two smaller non-negative matrices, A and B. The matrix B, on the right side there, contains what we call the basis components. So each row is a learned spectral pattern or building block that appears across the sample. And then the matrix A contains the coefficients or the weights. So we have one row for each sample, and it shows how strongly the components of B appear in each sample. And the algorithm starts by randomizing. So it starts with random non-negative values for both matrices and then kind of iteratively updates them, alternating between A and B to minimize the reconstruction error. And the process kind of continues until the product of AB gets close enough to the original data matrix. And there's a few ways to decide what's close enough. You can do, a maximum number of iterations. You can monitor when the reconstruction error stops improving, and that's measured with the Frobenius norm. Or you can use alternative criteria like the KL divergence, especially if you have probabilistic data. In our case, we used convergence of the Frobenius norm, which is kind of like a multi-dimensional version of the Euclidean distance. So that's how NMF works under the hood. But how does that all work in practice? Well, thanks for asking. Let's take a closer look at how the decomposition plays out for one fuel sample. Now, rather than relying on all 4,000 wave numbers directly, each sample is now represented as a small set of weights, which are the coefficients from the A matrix that I had before. And they describe how much of each basis spectrum of B contributes to that fuel. And then each row of B now looks like a mini FTIR spectrum. And many of these actually correspond to well-known functional group regions. And we found that often the basis spectra contained, heavily aromatic characteristics in one, or heavily alkene-like characteristics in the other, and so on. So they're kind of like grouped by chemical families, which kind of intuitively made sense. And because we use these coefficients as inputs to our machine learning models, we can track how each spectral feature influences the prediction. So by looking at which coefficients matter for each property model and linking them back to the corresponding basis spectra, we can gain valuable insight into what kinds of chemical features drive behavior like flashpoint or viscosity. For that, we need models, though. So the next step was training and selecting property models. Now, like I said, we used the coefficients from the A matrix as the input feature set. And then we experimented with a variety of model architectures, but ultimately chose to focus on random forest and extra tree regressors. And that was partly because they consistently outperformed others for us, but also because they're pretty robust to feature scaling and they provide built-in feature importance metrics, which was kind of nice when it came down to the interpretability side of things. And so what we did was just train separate models for each property and then evaluated them with a grid search over a range of hyperparameters, which included number of NMF components and then other like ensemble specific hyperparameters like, tree depth, number of trees, all of that. So that's represented by the middle panel on this slide. And then we selected the best performing model based on the validation set accuracy. That's the panel on the right. Where we have one final model per property paired with its optimal NMF feature set. So putting it all together, here's what the full pipeline looks like. We start on the left with the spectra, which we pre-process to get clean and normalized absorbance profiles. Then we apply NMF to extract between 2 and 30 features for each property. And then each of these features capture a recurring pattern in the spectra. Things like aromatic peaks or like alkane stretches. And then each sample is represented as a set of coefficients that describe how much of each feature it contains. And those NMF coefficients become the input to our machine learning models. For each property, we train ensemble models using different combinations of hyperparameters and NMF features. And we compare model performance on a validation set and select the best performing combination. And we do this for boiling point, flash point, freezing point, kinematic viscosity, and density. And then we have a smiley face, but mostly if the results are good. So let's look at the results. I like parity plots quite a lot because I feel like they're just so easy to understand right away. So here they are for all 5 of the properties that we predicted. We did see strong predictive performance, even on a pretty diverse data set that included neat molecules, SAF blends, and conventional fuels. Now, the results are competitive with prior work, and they're also particularly encouraging given the inclusion of blend data, which not a lot of people do and is typically harder to predict. We have mean absolute percentage errors between 2.7 and 4.6% for all properties except for viscosity. But that's mainly because the viscosity values are very small, and more than half of our data set lies between like 0 and 2, and so that really inflates that metric. But the absolute error for that was 0.23, which was pretty good, and so we were happy about that. And not only that, but a huge advantage of this is that we can look at feature importances assigned by the ensemble models and get a sense of what NMF features drive each property prediction. So each bar here represents one of the NMF features used in the final model for that property, and we've color-coded them based on their dominant compound class. So things like aromatics or alkanes, cycloalkanes. And we've done that based on the regions of the spectrum that they align with. And I'll show you that a little bit more in the next slide. Now you can see some interesting trends. For density, for example, the top feature resembles an alkane, which kind of tracks with the known relationship between branching and fuel density. And you don't need to read every color bar, there's quite a lot here, but you can see some clear patterns, right? Some properties are driven by aromatics, others by alkanes and cycloalkanes, and the number of important features varies too, as well as the kind of like distribution of those importances. Now, these trends often match what we expect from chemistry, right? Like aromatics lowering flash point or like cyclic structures really increasing viscosity. And so it gives us some confidence that the models are learning meaningful relationships. Now here, we're looking at the actual NMF components, and specifically the top ones for the properties. On the x-axis, you'll see wave number. On the y-axis, we have the normalized absorbance from the NMF basis matrix. And you'll notice that these features look like real interpretable FTIR spectra, right? Like they look a lot like that ethanol plot that I showed you earlier. And there's some cool things. For example, in the first plot on the top left, we see the top features for viscosity and flash point, which look a lot alike. Both show really strong peaks around a value of 770 on the x-axis, and that region is typically linked to like ring-shaped molecules like aromatics. It's kind of like a hexagon-like structure, and the specific motion picked up around the 770 range is kind of like a wobble or a bending of the hydrogen atoms that stick out of the plane. They stick out from the rings. Now, you don't really need to know the exact motion, just like that these patterns are strongly associated with aromatic shapes. Now, in contrast, in other plots, like the two orange ones in the middle, we see features peaking near 2900. And that region tells us that we're seeing like simple hydrocarbon chains, kind of like long strings of carbon and hydrogen atoms. And these are pretty common in fuel and more flexible compared to the rigid rings I just mentioned. So the cool thing is that the different properties are influenced by different structural or compositional elements, but sometimes they overlap. For example, both flash point and viscosity are linked to those ring-like structures, but boiling point is more affected by chain-like ones. And so it's not just about the prediction, but by looking at which features the model finds important, we can also learn something about the chemistry, right? It gives us some kind of clue about the molecular building blocks that tend to raise or lower a certain property, even in really complex mixtures. Now, all of this work has been integrated into the Feedstock to Function web tool. We have an Explore Blends tool on the left, which allows researchers to upload FTIR spectra for a new fuel or blend and then get an instant property prediction using the method that I just described. Or you could also select a combination of components and that we have spectra for, and then we'll do a little like linear by volume combination of the spectra, and you could also get properties. On the other hand, if you have properties in mind that you know you want to meet, we have a fuel finder page that can help browse blends and combinations of blends and fuels and molecules that meet those properties. And you can even select a pool of candidates and we'll show out of that pool the best combination to meet the properties that you input. We also have a paper that hopefully will come out soon. It will be published soon, so look out for that. Yeah, and that's all I have for today. So thank you so much for listening, and yeah, I'll take any questions now.